And we're back. Welcome back and happy Thursday. Today, we will continue on finishing out our segment on the network layer, looking at the APIs and an example of how to use them for the mechanism, i.e. sockets, that API for creating network applications. But before we begin, project number 2 will be due 1 week from today on the 16th of February, 2021 at 11:59 and 59 seconds p.m., 1 second before midnight. So why don't we begin? When we last left off, we talked about a case study for media streaming, in particular Dash, where a user, let's call him Bob, enterprises to watch a movie. So Bob logs into his Netflix account, he authenticates himself, and once he authenticates himself, he browses a number of Netflix videos. And so this list or catalog of Netflix videos exists on a server somewhere, and it's backed or run, hosted in Amazon Cloud. In fact, Netflix is a very large customer of Amazon AWS. And so within this cloud infrastructure, Bob is browsing the list of movies, and he goes ahead and selects a movie. Once he selects the movie, he gets a manifest file returned for the particular video he has requested. Now, beforehand, Amazon has uploaded multiple copies of this video to various CDN server instances. So there might be one on the West Coast, near various urban centers, and there's one that's particularly close to the region where Bob lives. And so Bob then gets this manifest, and within this manifest is all of the URLs for the different resolution versions of that movie that have been populated on each of these CDN server instances, as well as URLs to each of the instances. So not only for a single instance, Bob in that manifest knows or has URLs for the particular movie in different resolutions, Bob also has that URL for all of the copies that Amazon has placed. Now, of course, Bob then requests the video. And in requesting the video, his Dash client selects an instance of the movie and then starts its metrics looking at the quality of the stream. And should the quality of that stream start to degrade, it has two decisions to make. It will either revert to a lower resolution version of the video or select a different CDN server instance from which to download that video, to stream that video. Okay, so let's continue on and let's look at socket programming, both for the Unreliable service, UDP, as well as the Reliable Transport Service, TCP, or Transmission Control Protocol. And so the goal then is for you to learn at a high level how to build client-server applications. And the method that they use or mechanism is a socket. Now, of course, this is not a secure socket. That is something I would reserve for an application, maybe a final project, but this is just to illustrate to you the semantics that you use when the application interacts with this socket API. And so the socket API acts like a door between the application process and something called the end-to-end transport protocol. As we discussed when we talked about layering, each of these layers provides a service to the layer above. And the transport layer's responsibility, and we will learn about that in great detail in our module concerning the transport layer, which comes next. This transport layer's responsibility is to transfer all of those packets sent out by the application layer into the socket to transport them to the transport layer on the other side of this end-to-end communication between the two end systems or hosts that are involved in this communication. And so if the application on the left-hand side pushes a packet into its transport layer, so let's call that the outbound direction, that packet gets sent to and delivered to this socket on the other endpoint of the communication, this host or end system on the right-hand side of the slide. Likewise, the opposite happens if the process on the right pushes packet into its transport layer socket, and it comes out on the other side, delivered to the process of interest on the left-hand side or the left-hand endpoint in this communication. And so the socket, as described in the book, and I like that analogy, some might not, but I like the analogy. It acts like a magic door between the two application processes scattered between the host on the left and the host on the right. And it provides the so-called end-to-end transport because it provides a semblance of a guarantee. In the case of TCP, it is a guarantee. In the case of UDP, it is not guaranteed. But it provides some service, a semblance of a guarantee, to deliver this packet once it's in the doorway to that other doorway, magic doorway in a sense, on the other side. Now, of course, to the applications, they believe that there's a direct connection from one socket to another. You can almost imagine this magic doorway is connected to a weird transport hallway, like a wormhole on Star Trek. But nonetheless, this magic doorway is such that when you push a packet into it, it appears on the other side in the other doorway and makes its way out. When someone else pushes the packet, the other endpoint in the communication pushes the packet into this doorway, it goes across this magic hallway and appears or emerges out on the other endpoint of the communication out that socket. And so the socket acts like a door between the application processes, and this door uses this end-to-end transport for the delivery of that packet of information to the endpoint on the other side of this communication. So there are two types of socket, and therefore two types of transport protocol services. One is UDP, the unreliable service, and the other is TCP, the reliable service. Now, reliability means a couple of things. Both the guarantee that the delivery will happen, as well as this notion of order and non-corrupted. Everything will be delivered intact as you intended it. So that means that if you send a byte stream in certain order, that byte stream will be delivered, emerge out the doorway on the other endpoint in the same order in which you pushed it into the doorway on your side. And so an example application, and this is in the book, and it's in Python, it's not very complicated, but nonetheless it's still important to understand the semantics. And regardless of the language binding you use, whatever language API, it's usually some variation of this. And so you start out in this example, the client reads a line of characters from the keyboard, so you type in a message, and then the client sends this data to the server. Now, of course, the server is going to accept this data. It's going to perform some processing on it and return back the response. And that particular work that the server does on this request coming in from the client, it receives the data, converts the characters to uppercase, and then returns back the capitalized modified data to the client. So in step 2, the server receives the data, converts the characters to uppercase, and then it returns that modified data back to the client. And so that edge, or that round of the communication, where the server responds, it pushes this capitalized version of the string into its endpoint, its socket at the application layer, and then the client receives what emerges out of its doorway on its endpoint. It receives the modified data, the capitalized string, and displays this line on the screen. And so that is an honest-to-goodness client-server application. So let's take a look at what this might look like, and we will explore the Python code, which is in the book, that describes how this works. And so with socket programming, UDP, as we said, has no guarantees. It's a so-called connectionless version of transport layer services. And in UDP, there's no connection, as it were, between the client and the server. So there's no establishment of the connection. There's no handshaking. There's no round trip for establishing whether or not the endpoints have the resources to engage in a reliable communication like TCP does, because there is no reliable communication, no reliable transport. So there's no round trip for handshaking before the actual data is sent from the client to the server. And the sender explicitly attaches the address for the destination, the IP address, identifying the machine, or more correctly, the network card, for the endpoint on the other side, as well as a port number so that it identifies the application to which this packet should be delivered should it get to the other side intact. And so the receiver then gets this packet and extracts both the IP address of the sender, okay, as well as the port number from the received packet. And it needs that sender IP address because it might want to compose a response, and it needs port number because it needs to know to whom this particular packet should be delivered, which application is going to get it. And so UDP does not guarantee ordering of your data. Data can be lost, it can be received, or it can be received out of order. So if you send packet 1, packet 2 in that order, it doesn't always arrive as packet 1 and packet 2 in the same order that you pushed it into your end of the socket in the application layer. And so from the application standpoint, UDP provides unreliable transfer to the recipient, and it transfers groups of bytes or datagrams between the client and the server. So it's not reliable. And again, the reason why someone might use UDP is because their application can tolerate losses and they would rather have the speed. Now, everything comes at a cost in computer networking, and part of your job as a very good computer scientist and an engineer, if you're going to create network applications, is to understand what the behaviors are, the physics, if you will, of various components, and to be able to make the right trade-offs and choose the right components so that the system that you're building will have certain desirable properties. And so if your application can tolerate loss and could benefit from speed, then UDP might be your better bet for a transport layer. And so here in client-server coding, we have our server, and it's running with a certain IP address. And we create a socket instance, and that socket instance is usually some variation of a call that says socket. Now, of course, AFINet corresponds to the fact that it's an IP version 4 socket, and there are different versions of sockets that we have. And DGRAM stands for datagram, which means that it's the unreliable version of the socket. And so here, we create the socket, we get back a server socket instance. So now, once the server is running, the client then creates a socket, and you notice it's AFINet, so it's an IP version 4, and then a datagram socket is the type. So now you create a datagram, and you include in your datagram the server's IP address so that the addressing apparatus will be able to get this, and the switching core will be able to get this datagram to that machine or network card on that machine running the server process. And it adds a port number so that once that datagram arrives at the destination, the transport layer will know to which application in the application layer to deliver it. So it sends this datagram using this client socket, usually a client socket send method on that socket object or within that socket API. And so the datagram, if it makes its way across, wonderful, processing happens. If it doesn't make its way across, there is no response. You just don't get anything back from the server because it never received your request. And the underlying machinery for UDP is perfectly fine with that. And so let's assume the case where the datagram arrives successfully. This datagram is read from the server socket on the server side, and then it extracts the information from that datagram that it just read, and then writes a reply back to the server socket. And when it writes its reply, it specifies the client address and the client port number. And so the client gets the IP address of the server as well as the port number, and the client also inputs its port number and address so that the server knows to whom to send back that response. So the server sends its response, and let's assume that response gets back to the client. This client then reads that datagram from its client socket, special doorway. It closes the socket, extracts the information, and it now knows the response from the server. And so let's take a look at the Python code. The Python code includes getting the socket library from Python, and then we set the host name for the server and the port number that we need to contact the server. So now we create the UDP socket, identifying as a datagram and the version of the TCP/IP stack that you want to use. And then you go to the command line, and then you write a greeting, and then wait for someone to input a message. And so someone inputs the message at the keyboard, hits enter, and you compose that socket and send that message down the socket, pushing it through the doorway in the application layer side of the socket on the client endpoint in this communication. So you do a message in code to make sure that you're converting this ASCII to the right information wire format, and then you give the server name where you want this to go, and the port number, the application on that server to which you want it delivered. Now, of course, when you send this, the client socket send is also going to include information about the port number of this application running on the client, as well as the IP address. So now you do that send, and then you wait back for the response to receive whatever was sent to you as a response to the client by the server. So then you go ahead, you decode the message to get it from the wire format back to ASCII text, if necessary, and then you close the socket and you print out that message. All right, so you reply and you print out the message. So this is the server side. The server side, remember, is always running, it's always on. So you start out again and you import the library needed. The server chooses a port number, you create the socket. It's an IP version 4 socket, datagram, unreliable service. So then the server binds. And when the server binds, what it's doing, it's telling the operating system, okay, I am associated with port number 12,000. That's the link that allows the transport layer to know to deliver incoming messages to this particular server process. If you were a web server like Apache or an HTTP server, you would use port 80, but this is not a web server. All right, but that being the case, you bind, so you register it with the operating system, hey, associate me with port number 12,000. And so now you sit in a tight loop and you continually, again and again and again, remember the server is always on, you listen to that socket for an incoming request, and that socket is per connection. And so here we go to the server socket and we do receive from, and we choose a particular buffer size, and that buffer size, 2048, that's 2K, and you specify that buffer because the client server-side application needs to know how much space and memory it should allocate in order to store this data that's being read from the socket. And so now you get that information, and you have both the message as well as the address of the client that sent this to you. You decode that message, that's the work, and convert to uppercase, that's at the end, the work the server performs. And then once you finish performing that work, you send the response, the capitalized string, back down the wire. And that's the client's already waiting, doing a receive on that socket, and gets that uppercase capitalized string. All right, so the client has to initiate the connection, and with this connection in TCP, the client has to contact the server. So that means the server has to be present and running before the client is initiating or sending its request. Now the server in TCP has two sockets, and one is called the welcome socket or the server socket in Java. Now the client then contacts the server by creating a TCP socket. So this is the reliable service. So we're talking about TCP now. It specifies the IP address and the port number so that it knows how to contact or how to get the network infrastructure to successfully deliver this packet to the right machine on which the server runs and to that particular process, which is the server process. So it specifies the IP address and the port number. And now the client creates the socket, and the client TCP runtime establishes a connection to the server's TCP runtime, that layer, the transport layer. Now, when it's contacted by the client, the server creates a new socket, and that new socket is sometimes called a connection socket. And the connection socket is different from the welcome socket. The welcome socket's only purpose is for the server to recognize an incoming connection request is happening. Now, when that first round trip occurs between the client and the server, the establishment of resources is encapsulated by this connection socket. So the welcome socket sits in a tight loop, and listens for incoming requests. When an incoming request is satisfied, when the yes message saying, yes, I'm the server and I can perform these reliable actions. So here's my client, here's my server. First, the client says, are you able to communicate reliably? So there's that first round trip. And if I get a yes from the server, that yes edge is associated with the connection socket. And so for every incoming connection that is satisfied, the server can communicate at the other endpoint, a connection socket is created. So when it is contacted by the client, the server creates a new connection socket for every communication channel with a client whose request to communicate has been granted. And this allows the server to communicate with that client. So if you have a different connection socket for each client communication, you're able, as the server, to talk to multiple clients. And that's the reason why these resources are finite and a server can only support so many concurrent connections or so many users connecting to it with a web browser, is because at some point, after some number of connections, could be 1,000, could be 5,000, could be 10,000, could be more, the server no longer has the resources to grant these connection requests. And so you need the source port number and the destination port number, as well as the source IP address and the destination IP address, to note unique endpoints in a communication between a source and a destination endpoint. And so from the application standpoint, TCP, Transmission Control Protocol, provides reliable in-order byte stream-based transfer, and it acts like a pipe between the client socket endpoint and the server socket endpoint. Now, of course, as we go through the semester, you'll learn that it isn't a direct pipe. It gives you the illusion that there's a direct connection, although all of the layers acting together, the transport layer, the network layer, the link layer, and the physical layer, give the applications at the client and the server endpoints the illusion as if there were a direct pipe between the two applications facilitated by the sockets. All right, so let's take a look at the interaction with TCP. So you have your server running, and it creates the welcome socket, so-called server socket, as it's often called in Java, which it is called. The actual class name is called server socket. And you wait for incoming connections. So you call accept, and that means you're ready to try to listen for incoming requests. So at that time, the client creates its side, its client socket, and it gives it a host name for the server's machine, more correctly its network card, and a port number associated with the server process. And that should be the same port number that the server has called the bind routine on, because you want to identify a particular port number, and it should be the same port number that the operating system runtime for TCP is going to facilitate sending to whatever process is associated with that port number. So you specify the host name and port number, and then you actually get that connection establishment. That's where the handshaking happens in the first round trip that I alluded to. And so in that first round trip, you have your client and you have your server. You requested the connection, and then you get that response, yes. Now, subsequently, the client sends that text of the request. The server does some processing and sends back the response. And so it's this first round trip time that is represented with the server socket accepting that request from the client. And then one of the things that you return when you accept the connection on the server side is this connection socket. And it's this link between the connection socket and that client socket, which are the two endpoints in the communication between the server and this client that establish this connection. And that's unique for every client to server endpoint combination. And so now the client then sends a request using its client socket endpoint. And that corresponds to the second round trip. So this is the send, this is the processing, and this is the reply from the server. And so now the client sends its request. The server reads this request from its connection socket, and you'll notice this is the connection socket it's reading the request from, not the server socket. The server socket has done its job for this connection, and now the server is busy listening on the server socket for another client's incoming connection request. And so the read from the connection socket now on the server will get the information out of this socket doorway, which was put into its own doorway by the client. And so once the server gets this request, it performs some work or some action, and that action results in some value, and it returns the response, that result, back to the client as a reply by writing it to its doorway, its connection socket. So once it gets into its connection socket, that makes its way across the internet, across the network, and it makes its way to the client socket, and the client reads its side to get that reply. Client closes its end of the socket. Server closes its end of the socket after it sends the reply, and then client has the data, the response from the server, and client closes its connection. All right. So this is what it looks like in Python for the TCP client. And this is the initiator. You import the libraries from Python. Here's your host name for the server name, and you have a port number. And so now you create a TCP socket for that process running remotely on port number 12,000. First thing you do is create the client socket, AF INET IP version 6, and now you'll notice here the second parameter is no longer sock dgram, it's sock stream. A so-called stream socket is the reliable TCP service using a transport layer of transmission control protocol. So then you call connect on this client socket, and you give the server name, the host name, that's the machine or the network card, and the port number. And so now you go to the command line, get the input, and you now send to your, or through your client socket, the client side endpoint, you send that information that you obtained from the keyboard. You then go to your client socket and do a receive, giving it a buffer size of 1024, 1 kilobyte, and that's going to be where that information that comes from your socket, the response from the server, where you're going to store it. And so you get the modified sentence, which is the result of the action, the work done by the server on that request message that the client has sent. And then you print it out and you close your connection. So now let's look at the server for TCP. And so you start out, you import the library for TCP, for the socket interface in Python. You set a port number, and then for the server, you create your server socket. So it's AF INET IP version 6 sock stream. So now then you tell the OS operating system to bind, to associate me with a particular server port. And then you do a listen on the server socket. And so what this listen does is says, okay, look for incoming requests and satisfy them. So it goes into a tight while loop again and again and again. It does the following, and this is for each client that initiates a request. So you call accept, and when you accept the connection, that means you're allocating the resources needed for one instance of this end-to-end communication between the server and the client. So it gets a connection socket, and it's through this connection socket that the TCP server interacts with the client, and then you have the address information so you know where to send the response. So now you go ahead and you do the receive from the connection socket, and now you're reading the request that was sent by the client. And you give it some buffer size so you can store it, and you decode it so that you can convert it from wire format to ASCII format in this case. And so you then perform the work. So the work is to capitalize the sentence that you received from the client and its request, and then you send back this capitalized sentence, the response, back through the connection socket using a send, and sometimes it's listed as a write. And so then after that, the server closes its side of the connection. And so this is the server behavior in Python. So let's take a look at what this would look like in Python, and we'll actually do this for real. So let's transition to the command line. So I will meet you on the command line. So we're here on the command line, and on the right-hand side, we're going to put the server process, and on the left-hand side, we're going to put the client process. And so here, I have two Python files, a TCP server and a TCP client. If we look at the TCP server, it's exactly the code that we had discussed. And so again, we import our Python libraries for socket communication. We set a server port. We have our server socket command to create that socket. It's a stream socket because it's a TCP service, IP version 6. We bind to associate with the port number specified, so the OS reserves that for us, so that when incoming or outgoing packet or message is sent or received, it knows to whom to deliver it, this particular process, or from whom it's being sourced. And we listen, okay? So now we go into our while loop. We do the accept, so we accept the first round trip, the first connection request from the client, and then we go ahead and we read from that connection socket, and we get the sentence. We print out the address information and the sentence. We go ahead and capitalize it. We print out what the server is going to be sending, and then we go ahead and send it down the wire back to the client as a response and close the connection. So you'll notice here, the server socket, our welcome socket, once it accepts, all of this interaction with the client is done through the connection socket, and then the next time we iterate in this while loop, we accept another request. So let's take a look on the right-hand side. Let's look at the TCP client. Now the TCP client, just as we had discussed, we use the server name, and in this case the server name is a special IP address called the loopback address, 127.0.0.1, and that's a special address to use if the client and the server are on the same machine. The reason why you do that has to do with efficiencies that the TCP runtime exacts, and that is to use buffers on the machine instead of the actual network card as a way of getting faster communication. Why pay the cost of that extra load through the I/O system, which is slower, if you're not going to actually go off the network? And so here is the loopback address, and then we set the port number. We create the client socket. It's AF-INET, IP version 6, stream socket, the reliable transport service, TCP. We create our client socket and connect. We make that connection request, giving the server name and the server port. We go to the command line to get input. Someone types at the input, hits enter. You get back that text. You send that text down the client socket, first encoding it from ASCII text into binary format, and then the client goes ahead and receives whatever response was sent by the server, and then it prints out what the server's response was. Okay, and so let's go ahead and we'll run the server. So if we'll run the server, we say TCPServer.py, and of course, TCPServer.py. Oops, let's run Python TCPServer.py, and that's going to run. It says server is ready to receive. So now we'll run Python TCP client.py, and now it asks me, the client, for a sentence. This is my lowercase sentence. I hit enter, and you'll notice here the server received from address 127.0.0.1, port number 51093. That's the client. It got, this is my lowercase sentence, and it capitalized it, and that's what it sent back across the wire, the capitalized version. So now, on the client side, from server, I got, this is my lowercase sentence, and then the client exited. But the server's still running. Let me run the client again and type something else. My second lowercase sentence, enter, my second lowercase sentence. And so this is precisely the interaction that we talk about. There's the first round trip is the connection request, and then the second round trip is the request coming from the client, the server doing some work on that request, and then returning back the response, and we print it out at the client. Okay, so with that, let's go back to PowerPoint. I will meet you in PowerPoint. So that's our interaction between the TCP client and server, and the only difference between this and something like HTTP is that the message is not a simple text string that's capitalized. It involves a bunch of fields and much more sophisticated behavior by the server when it extracts the values of the various fields for the message format. And then if you're using secure HTTP, you're using the encrypted version, the secure socket version of your socket, so that all of this data on the wire is encrypted instead of in the clear, as would happen in this case. So with that, let's go forward, and this ends our study of the application layer. And our study of network applications is now complete. We talked about the architecture of network applications, how you lay out these processes that interact with one another on the end systems across a network. We had the client-server architecture, we had peer-to-peer. We looked at different requirements an application might have of the underlying transport, things like reliability, delay, and bandwidth. We looked at the Internet Transport Service Model, the Connection-Oriented Reliable Service, TCP, and the faster, non-guaranteed, unreliable datagram protocol. We looked at popular protocols, HTTP, Hypertext Transfer Protocol, and different variations on HTTP. We can use the header lines. We talked about email, Simple Mail Transfer Protocol, and the access protocols, POP, specifically POP3, and Internet Message Application Protocol, IMAP, and DNS, Domain Name Service, that is a distributed database that resolves IP addresses given names. And then we also talked about the reason for the speed up in peer-to-peer networks with an example of BitTorrent. We looked at issues with video streaming, content delivery networks, and then we ended with socket programming, examples for both TCP and UDP, and then we actually tried out the reliable service TCP at the command line. So with that, we've done a lot of stuff, and all these things give you the actors in a network. We looked at typical request-reply exchange, how the client is the role that requests info, and the server is the one that accepts the request, performs some work, and returns back a response. We looked at message formats, the fact that when you encapsulate, each layer is associated with header information, and we talked specifically about the message format for HTTP, what the header lines do. We looked at the data part. The data part is the payload on the client request response for HTTP, where you get the actual contents of the web page that you've requested from the web server. Different themes, there are messages and there are control messages. You can have things that are decentralized or centralized. It's important to make your protocol stateless. Stateless protocols scale, but if you have it stateful, you pay the cost with a slowdown in speed. And there's unreliable and reliable message transfer, and the big takeaway from application layer is that the complexity, and this is a deliberate decision, is kept at the network edge. That keeps the network core, so-called switching fabric, as simple as possible. And when something is simple, you can make it very, very high performance. So with that, congratulate yourself. We've covered a lot, and now we're ready to take a deep dive into the layers beneath the application layer, namely the transport layer, the network layer, and the link layer. So with that, we will end there. And as usual, please stay healthy, please stay safe, and I'll see you all on Tuesday.